Suprema and infima of sequences. We have already seen in the previous section the most general notion of supremum and infimum of a subset of the set of extended real numbers. So this time we are going to use that thing and define suprema and infima of sequences. So this section starts with this definition. Definition 631. Of sequences. Let be a sequence of real numbers. We define supremum of the sequence an written like this, or here we can, in fact it does not matter but the where the index is starting, but we choose to take it from some arbitrary integer n. We define supremum of this to be the supremum of this set. That is, we collect all the terms or all the elements of the sequence, we form the set consisting of those things, and that becomes a subset of the set of real numbers. So the supremum of this set is defined to be the supremum of the sequence. Similarly, we define infimum of the sequence to be the infimum of this same set. In this set, it is understood that n is any integer greater than or equal to n. So that is the definition of the supremum and infimum of a sequence. Now there is a remark regarding this notation. We can simplify this notation slightly. We sometimes write as more simply this and this respectively. So if we use these notations, then we have to write a little less than the usual cumbersome notation. Okay, now let us see one example that illustrates this concept. Let okay, this is not prominent, ink is needed. Let an be defined to be minus 1 to the power n. Thus, an, where n varies from n varies from 1 to infinity, anything you can take actually, is the sequence. Anything you can take means instead of 1 you can here put some negative integer also. Nothing much will change. There are only two possibilities. If your starting integer, if your starting point where the index is taking value is odd, then the sequence will start from minus 1. Otherwise, it will start from plus 1. So, for example, here 1 is odd, so minus 1 to the power 1 is minus 1. And then the terms or the elements of the sequence will alternate between minus 1 and 1. For this sequence, this set has only two elements, minus 1 and 1. Hence, supremum is 1 and infimum is minus 1. A simple example, but nevertheless it explains, it illustrates the notion. Another one, an is defined to be 1 over n. Thus, it's the sequence of the reciprocals of the positive integers. 1/4, etc. In this case, this set is hence supremum of the sequence is supremum of this set. Now this set has a maximum element 1, so that will be the supremum. And although this set has no minimum element, but one can prove that the infimum is 0, and in fact that is one of the exercises we have at the end of this section. The first exercise itself. This is 0. Notice that here the infimum of the sequence is actually not an element of it. Though the sequence becomes eventually close to it, and in fact the sequence is actually convergent to the infimum 0. So it is a little inaccurate. To say that the supremum of a sequence is the largest element. Largest element of it, and the infimum is the smallest element. In this case, it happens that supremum actually is the largest element, but that is not always the case, because you can see that here infimum is 0, which is not the smallest element of this sequence. In fact, this sequence has no smallest element. Another one, example 5. Well, not example 5, but item 5 in this section. Let a n be equal to n. Thus, the sequence an is just the sequence of positive integers. In this case, the set of the elements of the sequence is simply the set of all positive integers. Hence, the supremum is the supremum of that set by definition. Now, that is a subset of the set of real numbers which is non-empty, and it has no upper bound. It is not bounded from above. So, by the definition of supremum, this is equal to plus infinity, and infimum of an is equal to 1. If you are finding it somewhat confusing that we can sort of immediately write the infimum like this, you recall the definition of infimum. Infimum of a set E, which is a actually this definition also works for a general subset of the extended real numbers, but we don't need that right now. Let E be a subset of the set of real numbers. Infimum of E is minus supremum of minus C. So now, if you look at this set, say this is your E. Minus E is obtained by just negating all the elements of the set. So that means minus 1, minus 2, minus 3, minus 4, etc. Now this set has a maximum element, minus 1. All the other elements, they are decreasing. Okay, minus 1 is greater than minus 2, minus 2 is greater than minus 3, and so on. So the supremum of this set is minus 1. Now you negate that, you get 1. and this is the infimum. So infimum is 1. This way also you can think, or you can just simply think of the infimum as the greatest lower bound. This set has many lower bounds, but among them the greatest one is 1. So 1 is the infimum, and in fact it turns out that the infimum is actually an element of this set. However, this definitely is not an element of the set. It's not even a real number. So basically we are not doing anything new. We are just using the definition of supremum and infimum of a set to calculate the supremum and infimum of a sequence. As the last example shows, the supremum or infimum of a sequence can be plus infinity or minus infinity. That is possible. However, if a sequence is bounded, sequence in this context is a sequence of real numbers, okay, is bounded say by some positive real number m, then all the elements an of the sequence lie between minus m and plus m, because that's what boundedness of a sequence means, right? When we say that this sequence is bounded by m, it means that all the terms or all the elements of the sequence satisfy this inequality, which is equivalent to this. And that's why if we now consider the set of all terms of the sequence or all elements of the sequence, then that set itself will be bounded from above by m and from below by minus m, both of which are real numbers, because m is a real number. In that case, the set we want, we can take m here to have maximum generality. Actually, when we write some specific integer here, we don't essentially lose generality, but it looks nice if we write it in more generally like this. It feels like we are not losing anything. The set is bounded above by m and bounded below by minus m. Since this set is obviously non-empty, its supremum and infimum are both real numbers by the definition of supremum and infimum. When we have a non-empty subset of the set of real numbers that is bounded from above, then its supremum is a real number, and just like that, its infimum is also a real number when it is bounded below by a real number. Thus, the supremum of the sequence and its infimum are real numbers. That is, are neither plus infinity nor minus infinity. So that fact we can conclude if the sequence turns out to be bounded. Next we have proposition 636. Let least upper bound, it has a name also, least upper bound property we already have this name given to something else, namely we have already showed that the system of real numbers has the least upper bound property, but that is about sets, subsets of real numbers. This is about sequences of real numbers. A similar thing, but nevertheless it is different. Let an be a sequence of real numbers and let x be an extended real number. So x can be plus or minus infinity also. extended real number, that is an upper bound for this sequence. Well, not just an upper bound, but actually this. The extended real number defined by this. It is nothing but the supremum of the sequence. We have already seen in one of the examples that this can be plus infinity. So that's why we are saying it's an extended real number. Then we have an less than or equal to x for all n greater than or equal to m. All the terms or all the elements of the sequence have to be less than or equal to this supremum. So that is one thing. Also, whenever m is an extended real number, such that m is an upper bound for the elements an, that is an is less than or equal to m for all the indices n, then our x must be less than or equal to m. Then we have so the first part of this statement says that x is an upper bound for the sequence in the sense that it is greater than or equal to all the elements or all the terms of the sequence. And in the second part, we see that if we take any upper bound, capital N, for the sequence in this sense that all its elements are less than or equal to that m, then x must be less than or equal to m. So in this sense, x is an upper bound that is the smallest possible, so least upper bound. That's why least upper bound property. It's just like the property that we have already proved in the system of real numbers for sets. That is also true for sequences in this sense. Finally, for every extended real number, real number y for which y is less than x, strictly less than x, there exists at least one index n greater than or equal to m, of course, for which y is less than an, and an of course is less than or equal to x. So this final part says that x is also the least upper bound in the sense that nothing smaller than x can be an upper bound. Here y is an extended real number that is smaller than x, that's how we have chosen y. Then y fails to be an upper bound for the sequence an. That means we don't have this. This statement is false. So that means for all the indices this cannot be true. So there is at least one n greater than or equal to m for which an is not less than or equal to y. But by trichotomy then an must be greater than y. So that's what we have written here. Okay, so this is the full statement of the least upper bound property for sequences of real numbers. And its proof as usual will be seen in the exercises. It's the second one. Remark. So like the least upper bound, this statement involves upper bounds, least upper bounds, those things, supremum. There is a corresponding statement about infimum of sequences. There is a corresponding statement, or in fact we can say, instead of calling it statement, corresponding proposition. For infima, but with all the references on orders reversed. All the references to orders reversed. Example, in place of upper bounds we will have lower bounds, like that. And the proof is similar, exactly similar. which we will know when we see this exercise. Okay, now having seen these things, we now see an application of these concepts of supremum and infimum of sequences. We have already seen in the previous sections that if we have a convergent sequence of real numbers which is having some limit, then it must be bounded. Then one can naturally ask whether the converse is true. If we have a bounded sequence, is it convergent? And the answer, of course, is no. If you take this sequence, for instance, this alternating sequence, it is bounded by 1 and by other higher numbers, of course. But this is not convergent, we have already seen, because this is not a Cauchy sequence. However, if a sequence is bounded and at the same time it is either increasing or decreasing, then such a sequence turns out to be convergent. Such sequences whose terms or elements are either all increasing as you increase the index, or the terms or elements are steadily decreasing as you increase the index, they are called monotone sequences. Okay, the one that is increasing, that is called monotone increasing, and a sequence's terms steadily decrease, that sequence is called a monotone decreasing sequence. If such sequences are bounded, then they turn out to be convergent. This is not a monotone sequence, because you see here it increases from -1 to 1, but then again it decreases, then again it increases, like that it alternates. So this is neither increasing nor decreasing, it's not a monotone sequence, it fails to be convergent. But monotone sequences that are bounded are convergent, and that is the next proposition. In fact, this is the main result of this section. Proposition 638, monotone bounded sequences. Sequences converge, and the exact statement is this: let AN be a sequence of real numbers which has some finite upper bound. M finite means the upper bound itself is a real number. The upper bound is non-negative, that is understood, that comes from the definition of an upper bound, but it's a real number, it's not class infinity. And at the same time, and which is also increasing, that is AN is less than or equal to AN plus 1 for all n greater than or equal to m. This is the definition of a monotone increasing sequence. It may be somewhat confusing. If you look at this inequality, there is, we are allowed to have equality. Okay, an can be equal to an plus 1. To avoid this confusion, some people call such sequence non-decreasing. That is a sequence which either stays the same as you increase the index from n to n plus 1, either the terms stay the same or they increase, but they do not decrease. However, the name non-decreasing in itself is somewhat confusing. Some people will paradoxically confuse it with decreasing sequences. Okay, so it's better to call these sequences simply increasing, and the sequences where strict inequalities will be there throughout the sequence, they will be called strictly increasing. Okay, so increasing does not mean that the terms actually have to increase, but they do not decrease. For example, this constant sequence where the terms do not change at all, this is also an increasing sequence. The terms do not decrease, that is the point. Or for example, this sequence 2 2 2 3 3 3 4 4 4 etc., where they occasionally increase and then stay the same for some time and then they increase, but they can never decrease at any point. If that happens, then the sequence cannot be called increasing. Okay, so now our sequence of real numbers is increasing in this sense. This is the definition of increasing, and it is bounded above. Although the terms are increasing in this sense, none of them can go beyond n. All of them must be less than or equal to m. If that is the case, then this proposition says that such a sequence must be convergent. Then this is convergent, and in fact we can say a little about the limit also. And in fact, limit of an turns out to be equal to nothing but the supremum of the sequence an, and which of course is less than or equal to capital M by the previous proposition. So this thing will sometimes it will help us find the actual limit, but sometimes it's useful theoretically also. If you have to take an arbitrary increasing sequence somewhere in some situation, maybe in some proof of some other result. If it turns out to be bounded from above by M, that sequence, then you know by this proposition that the sequence is convergent, and not just that, you know that the supremum of the sequence is going to be the limit. So you can then use properties of supremum to find out further facts about the limit, which may be useful in that particular situation. And its proof also we will see in the exercises. It's the third exercise. And there is another version of this result that involves a decreasing sequence where this inequalities get reversed, and instead of an upper bound there is a lower bound. So that can also be proved. So the author writes, one can similarly prove that if this is a decreasing sequence, that is, if an is greater than or equal to an plus 1. Here also we don't have strict inequality. For some particular value of n you may have strict inequality, but in general we have this. In a decreasing sequence, the terms either stay the same in any step, or they decrease, but they never increase. One can similarly prove that if a decreasing sequence is bounded below by a real number, then it is convergent. And like here you have supremum, in this case you have infimum with limit equal to this. A sequence is said to be monotone if it is either increasing or decreasing. from proposition 638 and corollary 6117, we are now able to conclude something about convergence of this type of sequences, monotone sequences. A monotone sequence is convergent if and only if it is bounded. How? Proposition 638 says that a monotone sequence, if it is bounded, is convergent. If our monotone sequence is increasing, then boundedness means it is bounded above. You see, if it is given that this is a monotone sequence, increasing or decreasing we are not saying immediately, it is one of those two, but it is given that the sequence is bounded. That means there is some positive real number for which these inequalities are true for all n greater than or equal to m. That means these inequalities are true so that means if our monotone sequence is increasing, then using the fact that it is bounded above, proposition 638 implies it is convergent. And if it is decreasing, then using the fact that it is bounded below by minus m, which is a real number. Both m and minus m are real numbers. The version of proposition 638, this one can similarly prove that this part, using this part, one again concludes that the sequence is convergent. In the first case, in the former case where the sequence is increasing, it converges to its supremum, and in the latter case it converges to its infimum when it is decreasing. So if we have a monotone sequence that is bounded, then it is convergent. And conversely, if a sequence is convergent and monotone, then it is bounded. In fact, we don't even need monotonicity of the sequence for boundedness. If it is convergent, then it must be bounded. That we have already seen previously. So that's why boundedness is a necessary and sufficient condition for a monotone sequence to be convergent. Okay, that we can conclude from proposition 638, and corollary 6117 is just that thing, which says that every convergent sequence of real numbers is bounded. Okay, so we have got to this fact. So when we encounter a monotone sequence, we don't have to think of anything else. We see whether it is bounded or not. If it is bounded, then it is convergent, otherwise it's not convergent, it's divergent. Then there is an example 639. The sequence is infernal. We don't really know how the terms or the elements are appearing. We don't know the next term. But from our previous experience with the number pi and its rational approximants, you can see that these rational numbers, all these numbers are rational numbers, they are approaching pi in some sense. So this sequence, but that is not important whether it is approaching pi or anything. This sequence of rational numbers expressed as decimals here is increasing, and in fact the terms are strictly increasing, which you can clearly see. But all the terms are less than or equal to 4. No matter how many decimal digits you write here to increase the number, none of them will ever be greater than 4. In fact, none of them will be equal to 4. So that's why this is an increasing sequence is increasing and bounded above or bounded from above by 4. So by proposition 638, this sequence is convergent with a limit that is less than or equal to 4. The last line comes from here. We know that whatever the limit is, it will be the supremum of this sequence. Now 4 is already an upper bound, so you can think of 4 in place of m. So you know that the supremum, whatever it is, it will be less than or equal to 4. So that's what we have written here. Okay. Now, in spite of this somewhat nice looking, you can say, formula or fact, this is not always enough to know directly what the limit is. You have to find the supremum. But often, if you put some extra work into the situation, then you can find the limit, actual value of the limit. The thing that matters is that once you know that there is a limit, then you can use the limit laws from the first section, theorem 6119, to find the limit. And we are now going to see one such situation. So we are actually going to find the limit of a sequence which is not a single sequence but rather many sequences which are of a particular type. All of them have limit 0. Let x be a real number strictly lying between 0 and 1. Then we have this limit equal to 0. So this proposition says that this sequence, where you can start it from anywhere, we can start it at 1, say. This sequence is convergent and its limit is 0. So we are now going to prove this. This will not be left for the exercises, it will be proved now itself. We first show that the sequence this is x to the power n is decreasing. Since x is greater than 0, we have x to the power n also greater than 0. Oh, but we should mention also for any positive integer n. It's a simple enough fact, or if you want to really be rigorous, boringly rigorous, then you can prove this also by induction on n. So here what we are doing is we are multiplying n copies of x. All of them are positive, so x to the power n is also positive. So from the inequality x less than 1 we get x to the power n plus 1 equal to x to the power n times x. This is less than x to the power n times 1, that is x to the power n. For all positive integers n. This step there is no problem with this. This is your usual rule of exponent. In this step, what we have done, we have multiplied on both sides of this inequality by x to the power n, and it stays like this, it does not get reversed because x to the power n is positive. So that's it. X to the power n plus 1 is strictly less than x to the power n for all positive integers n. Hence, the sequence is decreasing. Also, our sequence is bounded below by 0. That is because we already have this, all the terms of this sequence are strictly greater than 0. Thus, by proposition 638, but not the statement that is given in the text, the version which has decreasing sequences. For in fact that is precisely written like what? For infima instead of suprema. Yeah. Converges to some real number, say L. Now, x to the power n plus 1 is equal to x times x to the power n for all positive integers n. So by theorem 6119, the sequence this is convergent and its limit is xl. Now, what is this? You see, this formula tells us that this sequence is a product of a sequence and a real number, namely this sequence and this real number. This is the convergent sequence and this is the real number. Its limit is L. This converges to L. So the product of the terms of this sequence and x, that will be a sequence, and that is the sequence x to the power n plus 1, this sequence. So that will also be convergent, and according to one of the limit laws, the limit of that product will be x times L. So that's what we have concluded here. The limit of this sequence is xl, and this also says that this sequence is convergent. But now look at this sequence, this one. What is the difference between this sequence and the original sequence, xn? If we write the terms of the sequence or the elements of the sequence, then these are the elements, x square, x cube, etc. Whereas if we write the terms of this sequence, then we get this. So you see that this sequence is just this one from which the first term has been removed. So essentially, this sequence is nothing but this sequence. And if you recall, in one of the exercises at the end of the first section, we have shown that if we remove any number, finite number of terms from the beginning of a convergent sequence, its convergence is not affected, and also the limit does not change. So we know that this sequence is converging to L. So removal of this term has given us this sequence, so that will also be convergent and that will also converge to L. So that means this sequence, or in other words this sequence, at the same time converges to L. We are now going to use that. And we will of course refer to that exercise. But before that, I think it will be better to mention this thing, that this sequence is actually that sequence. Note that if you want, you can use again n here, but that may cause some confusion. So by exercise, that exercise is 613, the third exercise of the first section, 6.1. Also converges to L. Now because limit is unique, if we now use that result, that limit of a convergent sequence is unique, then XL must be equal to L. Since a convergent sequence has a unique limit, we have xl equal to L, or x minus 1 times L equal to 0. Okay, so now we can conclude something. Now it is given that x is less than 1 and greater than 0. It is not equal to 1. So x minus 1 cannot be 0. Since x is less than 1, we have x minus 1 not equal to 0, and hence L is equal to 0. So that's how we finally conclude that the limit of the original sequence is 0. That is this is equal to 0. This limit is heavily used in analysis. Why I said that this is not a single sequence? It's not a single sequence. You can change the value of x. You get different sequences. All of them will converge to 0. The entire thing rests on the fact that x is positive and is strictly less than 1. And in fact, there is one line at the end of this section. So here the proof ends. Note that this proof does not work when x is greater than 1, and we will investigate this in more detail in the fourth exercise. So that ends the text part or the results of this section. After that we have the exercises, which we will solve in the next video. So I end the video here itself. So that means here we have come to know of that main result, which says that a monotone sequence of real numbers is convergent if and only if it is bounded. That is the main result of this section. In the next one, in section 6.4, we will see those notions that I talked about in the last video, that is upper and lower limits of a sequence, limit point of a sequence. I forgot about this section entirely, so I was saying those things in the previous video. In the next section we have those things. So we will see that. Tomorrow is Saturday, no? So number theory. So again we will go back to the proper number theory that we were doing back then. So until then, this is me, Lucifer, from a mathematical room. Have a nice night.